Alright, so what I'm planning for today, for this session, is I'll basically go over the practice exam or the previous year's exam that I posted. And there were a couple of questions on the homework on chapter 29 that I got questions about. Problem 51 in particular, no, 50 in particular. 51 not so much. I think 50 I got a problem, a few questions about, and 69. So I think I'm going to go over 50 with you guys afterwards. So I'll walk you guys through and hopefully we'll be able to finish it. But 69 is fairly simple. So I'll give you guys a couple of hints. So basically, part A, from what I've seen, not a lot of people had trouble with, right? Part A was fairly straightforward. Part B, so for part A, you have the force. You calculate the force for the magnetic field. And you know it's in the opposing direction of velocity. So force equals ma. So you find acceleration, integrate, apply the initial conditions for velocity, and you find the actual function for velocity. Integrate it again, and you find the position. And for the position, you can apply limits because you're integrating with respect to time. So time goes from 0 to infinity. It doesn't matter there, and you can find the answer there. So it's not. I mean, it does require a couple integrals, but these integrals are fairly simple. But yeah, it shouldn't be too bad. All right, let's get started. So how many of you guys looked at the exam? A good amount. How many of you guys actually attempted to do the exam? A couple. All right. So going through, problem 1 was straight from notes. This is some, and then problem 2, homework. I'm not sure you guys did that problem. 3 was homework problem. 4 was a cool problem. So basically for 4, magnetic field stays constant, but the area increases. 5 was verbatim from lecture. 6 is just stupid easy. 7, you guys should be, it's a bit more complicated, but we'll go through that also. And 8 was more relevant for last year this time. So all right, so problem 1, does everyone have a copy of it printed out? Do you guys know what I'm talking about? Let me bring it up. Oh, by the way, the last 2 lectures are also up online. I posted them today. I also posted the formula sheet that's going to be used right here. And exam. You guys all read? Oh. All right, so problem 1, you have a straight current carrying conductor, basically a straight wire. Can you guys read that? No. Better? All right. So you have a straight current carrying conductor with current I and length L, and you're assuming axial symmetry, so the wire itself has cylindrical symmetry. Find the magnetic magnitude and direction of the magnetic field distance x away from the middle of the conductor, and I gave you the form of the integral for that. So what do you have here? You have this, again, straight from lecture notes. I think first year I did this. Length L, so let's say this is 0 point, so it's L over 2 minus L over 2, some point P here, current going up there, so this is my distance x, calling this angle phi, this would be pi minus phi, and this is this part here is y, so this is r equals square root of x squared minus y squared, or plus y squared. This is my x-axis, y-axis. Now for this, we encountered this last time. We don't have symmetry to exploit here, so we can't use Ampere's law for this. So we would have to use Biot-Savart law, right? So I mean, that's one of the reasons I gave this problem, so you can test and make sure you guys know Biot-Savart law. So it makes it a bit more difficult, but we do know what Biot-Savart law is. It's B equals mu naught I over 4 pi integral of what? I dl, well, I is already there, so dl cross r hat over r squared, right? dl cross r hat over r squared. Now this thing in particular can also be expressed as dl cross r vector over r cubed, right? You guys know where that comes from, right? R vector basically is equal to r times r hat. It's in the r direction, radial direction, and if I'm dividing this by r cubed, this divided by r cubed, this goes away and I get r squared there. So you may see this written in a different form, but just know that these two are essentially the same. So using that, I know what dl is in that direction, radial direction is there. So when I do the cross product, I get mu naught I over 4 pi. Integral goes from negative L over 2. L over 2, I'm doing it over y. So I have x dy over x squared plus y squared to the 3/2. And there's a more thorough derivation of this in the notes, and you should look at that if you still have some trouble. But then again, this basically comes from this. You have magnetic field, we're saying is mu naught I over 4 pi, integral from negative L over 2, L over 2. This is x over x squared plus y squared to the 1/2 times dy over x squared plus y squared. So this is my r squared, and this is the other term. So now I integrate this and apply the limit. So the integral form, I believe, is given to you there. So you apply the form and you get b equals mu naught I L over 4 pi square root of x squared plus L squared over 4. And the direction for this is, well, current's going this way, so which way is my magnetic field going to be in? So it's x, y, so positive z is coming out this way. So magnetic field is going to be in my negative z direction at that point. Right, so and the direction is negative z hat. So you may either express this in terms of give me the magnitude and then afterwards specify the direction. So it's not always going to be clear cut as to the direction. It can be one of those loop things where it's going into the page. So you may not have a clearly defined axis, and at which point you can give me the magnitude and then do something like that or something, or specify, write down the direction. Or you can just express it in terms of a vector, which is what this is. Now, second part of this find the magnitude of be a distance r if L is much larger than r. So basically you're looking at the approximation you're taking is that the wire is almost infinitely long. So for that, so if L approaches infinity, we basically take that thing and rework or plug in the infinity there. So now what we have is the magnetic field comes out to be mu naught I over 4 pi L over x squared plus L squared over 4. Right? Now this is to the 1/2. So I can factor out the L squared from here. So what I would get now is mu naught I over 4 pi L over, if I factor it out, I get L times x squared over L squared plus 1/4. Right, so that's what I get from that. These L's cancel out. So as L approaches infinity, this term goes to 0. Right? So what I end up with here is mu naught I over 4 pi times 1 over square root of 1/4, which is 1/2. So I'm essentially multiplying this by 2. So I get mu naught I over 4 pi. Cancel out the 2. So that's my magnetic field when the wire is really long. Again, so this is the issue last year. These points that I assigned for this are almost arbitrary, not entirely arbitrary, but more or less arbitrary. So if a problem seems easy, but it's assigned like 50 points, it doesn't necessarily mean that there's a hidden trick to it or something that I expect you guys to know. I want the numbers to work out to a nice even number that if it's out of 100 points, then I just got to balance out the stuff somewhere. So it is entirely possible that easy problems may have a higher value. So just keep that in mind. So don't get stressed out if you see an easy problem followed by a huge point value. The point values don't mean anything other than the point values assigned. But all right. So this problem, you have another conductor 2D away, and also has a current flow I, but it's in the opposing direction. And we derive the magnetic field from it. Well, this is a simple case of superposition. Right? So if I have first current, it's coming out, so which means that my magnetic field is something like this. If it's coming out, right-hand rule dictates that it's going counterclockwise, and if it's going into the board, that's the opposing direction. This is going to be going clockwise. Right? So over here, I have the magnetic field going up, and over here I have the magnetic field going up. So if I'm looking at the magnetic field between these two wires, so exactly in the middle, well, we know what the magnetic field is going to be a certain distance away. We just plug in D for that, and whatever magnetic field this contributes, the other wire also contributes the same amount because it's the same amount of current and it's in the opposing direction. But in this point here, they'd both add up. So what I essentially end up getting is if my B over there for long conductor is well, from wherever, so it's we know that it's mu naught over 2 pi times the distance d, right? So and we have two of these, so we multiply by 2 essentially, so we just get mu naught over pi d. Right, does it make sense? The what? That's a good question. There should be a current. All right, so let's look at the next question. I like this question, the upcoming question. All right, so a straight piece of conducting wire with mass m, length L is placed on a frictionless incline tilted at an angle theta from the horizontal. There's a uniform vertical magnetic field B at all points. The voltage source is attached to the end of the wire, blah, blah, blah. Draw 4-pi diagram. So you got to clearly define your axes, resolve any vectors that you need to. Find the magnitude and direction of the current that has to keep the wire from sliding down. Okay, so the free body diagram for this, if I'm looking at it from this side, I would have something like this, right? And so here's my rod, current coming out, I'm saying. So the magnetic field, because it's coming out over here, is going to point up. And the normal force is going to be perpendicular to this surface, so I have my normal there. Mg is going to go straight down. And the force I want due to the current is going to be in this direction. Call that Fi. We know that, or you know also from chapter 27 it should be, force is the current length cross B. Now I just sum up all the forces, so what I have here in the x direction, I have this force there, but if I make this my axis here, like that, then what I have here is Fi cosine theta minus mg sine theta equals 0 for the y direction. Or before we do that, I can solve for Fi here. So Fi equals I LB sine of theta. So this theta we know is 90 degrees because they're perpendicular, this force and the current. So we know that this is pi half, so therefore this term goes away to 1. So this is my force due to the current. And I plug that in, so I get I LB cosine theta minus mg sine theta equals, well, not sorry, equals 0, but I'll bring this over, so this goes to I equals mg over lb cosine over that's tangent theta. All right. So that's my current, and then right hand rule will essentially give you the direction. So well, basically the way I know if my forces has to be this way, I know that my current has to come out. So yeah, easy problem, right? No one thinks it's easy? Yes. This one? So that's the force here, right? Fi. So I know that it's I L cross B. L and B are perpendicular. So this essentially what ends up happening is it's I L B sine of the angle between them, and that angle is pi halves. So this term goes away. So when I take this Fi and plug it into here, and solve for I. All right, consider solid coaxial conductor with radius A, insulated, okay. So central conductor, so this middle one carries a current I, and then this one also, the outer one also carries a current I, but their directions are opposing. The currents are distributed uniformly over each conductor, derive an expression for the magnitude and the magnetic field at outside the central solid conductor, blah, blah, blah. All right. So given that diagram, let's first calculate it for the case where A is less than R is less than B. Right, so we're calculating it for the region here. Now what law would we use here? So we're calculating magnetic field. So when you calculate magnetic field, what two laws do you have? Beer's law and Ampere's law. And which one should you use here? Ampere's. Why? Yes. You have symmetry that can be exploited, so you should use Ampere's law here. So we know Ampere's law is B dot dl equals mu naught I. Right? In this case, I take my surface to be cross section of that wire. So essentially, my B dot dl boils down to 2 pi r, whatever my r happens to be. Now, over here, for this case, whatever my current that's penetrating is the entire I. Or I enclosed or I penetrating is simply I, because I'm looking at the case where the conductor is below my surface or less than my surface. So the entire, so if this were my conductor, current's coming out, I'm picking my surface to be something like this. So all the current is penetrating my surface. So from here, you know that that's I, so therefore B dot dl equals this. So from here I can solve for what my magnetic field is. So times B. Magnetic field equals mu naught I over 2 pi r. Right, so this entire I is included in there. Now, for C, sorry, for the second part, it's asking for points outside where R is greater than C. So I have my conductor there. That's the one that's coming out of here. The next one, I have something like this. Right, so this is some solid piece. So this is my radius A. This is B, and this is C. So I'm looking at a surface that is outside all of this. Well, off the top, what do you think the answer is going to be for the magnetic field? 0, right? Because for my eye enclosed, I have the eye that's here, the inside conductor, and the eye that's in the outside conductor, and they happen to be the same. So my eye enclosed equals what? That eye there minus the other eye equals 0. So therefore, when I look at my magnetic field, integral of E B dot dl, this equals to mu naught I is 0, so this whole thing equals 0. So that's for the second part. Same setup, but here the current in the central one is I1, and the current in the tube is I2. So they're different currents now, no longer the same. And the currents are both flowing in the same direction. So they're both flowing in the same direction, and I'm saying they're flowing to the right, so the other way. Derive an expression for the magnitude of the magnetic field. Okay, in the center part and the outside part. Okay. So center part's what? We already essentially solved for it. If the current inside is I1, then simply add a 1 there. And there you go. Answer's done. Right? For the second part, it's no longer 0. So what is this going to be? I mean, it's still more or less the same. Right? I have my outside surface here. My current inside, and they're both going in the same direction. So my current is now going to be I1 plus I2. So that's my current. I plug that in. So what I end up getting here is simply the same as this. I get mu naught I over 2 pi r. This equals to mu naught I1 plus I2 over 2 pi r. Right? So far it seems to be an easy exam. And it was. And as I mentioned during one of the lectures, I think 5 out of the 7 questions were verbatim from the practice exam, so they saw everything. But they still did not do well, so that was really disheartening. But I won't give you guys the same exam again. Okay. So for this, now this is a cool problem, I thought. What we have here is semicircle, and we varied magnetic fields, but here you can see that the area varies. So what happens here is you have a wire, magnetic field that's going into the page, resistor here, and essentially this completes the circuit. So you got a magnetic field coming out of here, and you have a current that's going to be induced there. So as this rod moves about, which is moving at a constant frequency, the magnetic field changes, which means the magnetic flux changes. Therefore, you'll have a current induced, and you got to find the current induced. And again, I said my final answer should be in these terms, so there's no confusion. So let's do that. So we have this is length L, so that's sort of the radius. This is my resistance R. This is the point P at which they pivot, and this rod is moving at a frequency of omega. And you have a constant magnetic field that's going into the page. Now, this particular formula that you guys should know might be useful. So if I have some piece, some wedge, some arc, right? So this is some angle theta, and this is some radius r. I'm looking at some arc s. The arc length s equals r theta, right? And the area for this is pi r squared, but I'm looking at a fraction of the actual circle. So to calculate the fraction of the area, well, I know the total angle is 2 pi. So I have a certain angle theta over 2 pi. And that's the fraction of the area that's that I take into account. So in this case, I know that, well, the area is pi r squared times that. So I basically get L squared over 2 theta equals the area for this part. Now for the flux, I have integral of B dot dA. Open surface or closed surface? Open surface. Flux is always open surface. What happens when you close the surface for this? 0. Exactly. What happens when you close the surface for electric flux? It's Gauss's law, right? This equals to the total charge enclosure over epsilon naught. So fluxes are always open surface. This equals 2 phi b equals BA. So B is in this direction. A, well, is also, I'm saying, in the same direction. So, because we know, okay, magnetic field is going in this direction. So, in principle, the current would be induced in this direction, right? Magnetic field is in this direction. But we know that it actually would be the other way around because of Lenz's law. Right, so magnetic flux, my magnetic or area is L squared over 2 theta. So I get B L squared theta over 2. Now I change this. So I have my phi. So I'm looking at d phi b dt. This equals to d over dt BL squared theta over 2. Now theta changes. So what I get here is BL squared over 2 d theta over dt. This thing is basically omega. So this equals to BL squared over 2 omega. I am missing something here. Am I? No, I'm not. And this is the EMF, but that's the magnitude of the EMF. So now I can, now that I have the EMF and I say there's a resistor there, it's not terribly difficult to calculate the current. Right, so the current, Ohm's law states that EMF equals IR, therefore the current equals EMF over R. So essentially take that and divide it by R. So therefore my current induced is equal to B L squared omega over 2R. Direction is, we know that the magnetic field is going into the board, which means that the current normally would go clockwise, but Lenz's law dictates that it has to be the opposing direction, so it's counterclockwise. So direction for this, counterclockwise. All right, 5 is in my notes, so I think I'm going to skip over that. It's also on the lecture videos because we only have 20 more minutes, and I want to go through the homework problem you guys had trouble on, problem 50. So I'm going to skip problem 5. It's, like I said, verbatim from the notes. So all the equations, everything should be the same. So I'm going to skip over this. Problem 6. So 5 we're going to skip over. 6. All right, current I goes through the rectangular loop, and there's a magnetic field, a uniform magnetic field B, as shown, perpendicular to the paper. It's coming towards you. What is the torque on the rectangular loop? Well, we know that the torque is equal to, well, it's a vector, equals to mu cross B, and where mu is I times the area vector. So in principle what it is I A cross B. I believe you guys did this in chapter 27, right? So now my magnetic field and area are, either way you look at it, either whatever direction you take the area vector to be, they're parallel. So therefore the cross product between them is going to be equal to 0, which means that there's no torque. Right, so easy problems. Yes. So what I have is something like that. Current is flowing in this way, coming out this way. Right? So given the normal convention of the currents going in this way, I'm going to say my dA vector is this way. Right? So far so good. My magnetic field is also in the same direction. Right? Okay. Now torque is defined by mu, which is the moment, cross B, the magnetic field. Mu is defined as the current times the area vector. So that's the vector there, mu vector. Now, so what this boils down to is the current I times the area vector A cross B. Now, these two vectors, area vector and magnetic field, are in the same direction. So the cross product between them is going to be equal to AB sine of the angle between them. Sine of the angle between them is either 0 or 180, but in this case it's 0. For either case, the cross product is going to be 0. So the answer is 0. I mean, if you want to think about it this way, you're looking at the torque on this thing. So you have this rectangular thing, it's going to be, if there was an actual torque on it, it would rotate something like that, or the other way around, right? But you have uniform field throughout, so it's logical to say, look, I mean, if the field is uniform throughout and magnetic and the current is uniform, then there's not going to be any torque there, because basically, if anything, it'd be magnetic field would might push it up or bring it in, but it would be balanced. It's not imbalanced to create a torque, which is another way to think about it. But that's equations tell you the truth. All right, so next we have the LRC circuit. We'll go through this real fast. So there's not a whole lot of complicated things I can ask you about the LRC circuit. Now, you have the circuit here, certain potential, resistor, inductor, self-inductor, capacitor. So the inductor and the battery are ideal, so there's no internal resistance there. The switch is opened at time t equals 0 after having been closed for a long time. So what happens after the switch is closed for a long time? What's that? The capacitor will be fully charged, and the inductor will be overpowered by the current, and it will also reach Imax. Right? Now, okay, so what's the EMF in the inductor right before the switch is opened? Zero. Right. So whatever you look at it, there's no EMF in the inductor, so electric field there is 0. What is the energy stored in the inductor right before it's opened? Well, energy, we went over this, it's 1/2 I L squared, right? So we know it's right before the switch is closed, so it's basically the current flowing through there is going to be I max, the maximum current. So my I is going to be VB, right? That's the voltage of the battery divided by the resistor I have that's in series with the self-inductor. So that's my current. So is it IL squared? No, sorry, it doesn't make sense. I squared L. Okay, so my energy U is going to be equal to 1/2 VB squared over R squared L. All right, after the switch opens, what is the peak value of energy that will be stored in the capacitor at later times? Well, the capacitor and the inductor are parallel, so therefore the energy between them will oscillate between the inductor and the capacitor. So it will basically be at some point basically be the same energy here. Part D. Find the current in the inductor at the time t after the switch has been opened. Yes?
Do you expect us to rewrite a variable that we've already defined somewhere else? Like let's say we had already defined I. Do you expect us to rewrite u in terms of, or can we write u in terms of I?
No, because it has to be in terms of what's given to you.
Okay.
So if in this problem over here I gave you VB, R, L, and C. So the final answer should be in terms of what's given to you. I mean, just to keep all the grading, everything simple. Because if you've defined it somewhere else, obviously I know that you know it, and you know that you know it. So 2 extra letters, so not gonna make a difference. But I mean, having said that, I don't think I've had a case where that's happened. But if you actually define it somewhere on top or something, then if I catch it, then obviously I'll give you the full points. But I want you guys to actually write it down in terms of what's given to you.
So right there on part C, we said after this, like opening the switch was the peak.
Mm-hmm.
Basically, after we open it, it's just gonna keep the energy's gonna keep going down. So
It's going to keep going down. So the energy, a certain amount of energy in the inductor, right? Once the switch is opened, what's going to happen? There's going to be nothing flowing through the resistor. So it's not technically going to die down. I mean, in principle, in reality, it will, because the wire itself will have some resistance. But this is an ideal case, and the capacitor doesn't have any resistance, so it'll alternate back and forth. So the inductor will get, if you want, discharged, charge at the capacitor, and vice versa. We covered C, D. Find the current in the inductor at some time t after the switch has been opened. Well, because it's going to be oscillating back and forth between the capacitor and the inductor, this is going to be sinusoidal or cosinusoidal. So my current I is equal to I naught cosine omega t, where my I naught is my I max, which is VB over R. So my current I is going to be VB over R cosine omega. Here I can define in terms of L and C. It's going to be T over square root of LC. And I believe this formula, or at least what you need there, should have been given in the formula sheet. So I'm just going to find it. All right, and last one. Again, like I said, this is more relevant to last year's exam. I gave it, this exam was the day after, or Monday after Dark Knight came out. So, I mean, we all know the answer is C. But, I gave points for answering the question. So last year, a movie came out Friday. I gave the class the option to take the exam on Friday or Monday. They chose Monday, obviously. I mean, I told you guys in the beginning, right? I can move the exam 1 or 2 days here and there. It doesn't make a difference to me. So, but you guys should have voiced that, sometime, a few days ago at least. So I could have made arrangements to move it and all that. I mean, it's still not too late. I mean, if you guys can get the whole class consensus to move it, that's fine with me. It gives me more time to write the exam. What's that?
Is that a good thing or bad thing?
I don't know. It's whatever it ends up being. Like I said, I mean, we got to be careful what you wish for. In undergrad, I was taking my E&M class, and the professor was this German guy, that really smart guy, nice guy too. But his exams and homework, especially his homeworks, were ridiculously hard. I mean, just ridiculous. So I had him. So UCLA was quarter system. So I had him for this upper division E&M class was spanned over 2 quarters. So I asked, second quarter, I asked him, hey, look, your homeworks are tough. You know that, I know that. So how about you assign more weight to the homework? So, because we spend a lot of time on it. And he's like, sure, I have no problem with that. And let's ask the class. So he asked the class the next lecture, and most of the class was okay with it. And then I said, cool, now it's worth more, so I can come up with more interesting problems. I was like, oh, man. So actually, my homework percentage ended up being lower than my exam percentage. Gotta be careful what you wish for. All right, so has everyone here attempted problem 50? Right. It is not an easy problem by any means, but it is doable. So let's go through that. Alright, so we have, basically it gives you a circuit, capacitor RC circuit, and puts it in a battery and a switch. So you have something like this. Alright, so minus plus. There's some capacitor here. resistor here. Goes in, switches there. And it tells you that the only contribution that comes from this, so obviously when I close the switch, current's going to flow this way. And I have another loop here, dimensions A and B, and the distance between these two is C. And the magnetic field, so if my current is going up like that, right hand rule dictates that it goes into the board. And I believe they give you what resistance per meter for that, for this thing, right? Okay, so if you have a total length of L, so R over L equals 1.0 meter. We know that N is equal to 25 turns. So for a charging capacitor resistor circuit, you guys should have done this in the first half. The charge equation as a function of time would look something like this. So I have Q 1 minus e to the negative t over tau, where tau equals R naught C. And this is my Q final. So my Q final is equal to capacitance times my EMF. And the EMF there is also given to you. I'll label that. We'll have two EMFs. I'll say this is EB. That's whatever E. So I know my current I is a time derivative of charge. So this is going to be Q final over tau e to the negative tau over, or t over tau. And this is going to be equal to QF, that's going to be equal to C epsilon B over R naught C e to the negative t over tau. Capacitances cancel out, so I get epsilon B over R naught e to the negative t over tau. Alright, so far so good. This gives you the current as a function of time for the charged capacitor. Now, we said that the magnetic field was created, or any appreciable magnetic field is created by that wire on the left. Sorry, yeah, right. Wire on the right, and that's the only one that creates any appreciable magnetic field. So we can come up with something for that. So the magnetic field, B field, we calculated this way. It's only caused by that, so we know the magnetic field of a long current carrying conductor. That is B equals mu naught I over 2 pi R. Right? It's given to you at this point. You've used it enough where it's second nature, hopefully. So now I can plug in stuff. The magnetic field is going to be mu naught over 2 pi R EB over R0 e to the negative t over tau. Now I need to calculate the flux. My magnetic flux is equal to integral of B dot dA. So for that, the dA vector is obviously going to be, well, we'll say it's coming out. So we would have, and of course it has n turns, so this is going to be equal to n mu naught EB e to the negative t over tau over 2 pi R naught. And of course we have to integrate B over R dr. It goes from C to C plus A. So start off at C to C plus A. So basically what I'm saying is my dA vector is equal to, it's in the z hat direction, and B dx for that small circuit. So the flux ends up being n mu naught EB e to the negative t over tau over 2 pi r naught times B log of C plus A over C. Again, I express my natural log as log because whoever actually uses log base 10, right? Everyone uses natural log. So, or not everyone, but I mean, for all intents and purposes, natural log is log. If it's log base 10, I'll specify it otherwise. So that gives me my flux. So as Faraday says, I don't care about the flux. We care about the change in flux. So I differentiate this. So my change in flux, which is epsilon, equals negative d phi b dt. This is going to be equal to negative n mu naught epsilon b times b log of c plus a over c, all over 2 pi r naught, and I have the e term there, so what I would have when I take the derivative of that, I get negative 1 over tau. So I get negative 1 over tau e to the negative t over tau. Right, so the negatives cancel out, and then tau we know is r naught c. So what I end up getting now is n mu naught epsilon b log of c plus a over c over 2 pi r naught squared, r naught times r naught c, times e to the negative t over r naught c. Right, so that's my EMF. Which I ate it up. Sorry. Yeah, so the B is still there. Now I have my EMF. I need to come up with what my current is. So my induced current is going to be I equals B over R naught e to the negative t over tau, because it's an exponential function. So this ends up being log of I R naught over epsilon b equals to negative t over R naught c. So therefore, time it takes is R naught c log EB over I R naught. And then you plug in and you calculate the current. Right, you plug in, I'm sure you guys have different numbers. So at least, but the numbers should be around the same order of magnitude. For the numbers from the book, once I plugged everything in, I got 1.83 milliamperes. And for the direction of the current, well, we know that this is the current. Magnetic field is going around this way. So in principle, we would think the current would be clockwise, but in fact, well, it should be clockwise. It's clockwise. It's actually no, but the flux is decreasing, so it'd be the other direction. Yeah, so it is clockwise. So the direction is going to be clockwise, at least for the numbers in the book. All right. So I essentially did a homework problem for you guys now. You just gotta go home and plug it in, but it's there. All right. So the notes still aren't updated. I haven't had time yet, but I will update it today, at least up until Monday's lecture, and then tomorrow we're going to start EM waves, Maxwell's equations, and all that. So that won't be up until sometime during or after the midterm. All right. I'll see you guys tomorrow.